Alright, so today I'm going to be reviewing basic integration. Alright, so what is integration in the first place? So let's say we have a little graph here, right? And so we have our function, we're going to have a green function, or just something like this, right? And the idea is that we want to find the area under this curve, right? So let's say from x equals 0 to some value here, and we want to just go up to the curve and find all of this area. We could do that with integration, and so I'm going to teach you some of the basics of that today. Alright, so this is after the concept of derivatives, so if you do not know derivatives, you might want to learn that first. But the idea of integration is it's the opposite of differentiation, the opposite of a derivative. So if you have something like x squared, we know that to take the derivative of it, what we do is we take the power, we move it to the front, then we subtract 1. So x squared will become 2x. And if we have a function like x cubed, we take the power, we take the derivative, we move it to the front, and then we subtract 1 from the exponent. So x cubed will become 3x to the 3 minus 1, which is 2. So 3x squared. So that's what the power rule says. So now, with integration, you're going to do the exact opposite. Okay? So if we have the integral of, let's try that again, the integral of 2x with respect to x, that's what the dx means, we're taking the integral with respect to that. We know that the integral is x squared. The idea is that we're going to do the opposite of the power rule, right? So what we did before is we took a number like x to some power, so x to the n, and then we said now instead we're going to have nx to the n minus 1. So how would we go from here to here? So the idea is that we're going to add to the exponent 1, because we subtracted 1 here, and then we're going to divide by that exponent. So if I said 2x, we're going to add 1 to the exponent. So you can imagine like x to the first, right, is the same thing as x. So if I said x to the first plus 1 is now x squared, then we're going to divide by that exponent. And so we are left with the integral of 2x with respect to x is just 2x over 2, which is just x, to the 1 plus 1, which is 2. So like we saw before, that when we differentiated x squared, we get 2x. But when we integrate it, we get x squared. However, we are not done, because this is the indefinite integral. And we know when we differentiate a constant, like, for example, 5, right, if you took the derivative of 5, you get 0. And so, if we had something like x squared plus 5, and we differentiated it, right, we'd get 2x plus 0. And so, you have to account for this whenever you integrate it, because you don't know this. There could be another value that's added onto there. And so we just put a plus c to encompass all of these ideas. So let's do another problem for practice. Alright, so we have the integral of 2x minus x squared dx. Okay, so how do we approach this? What we could do is we could separate this integral if we wanted to, saying that this is the same as just breaking apart the integral, and we could rewrite this, right, and saying this is also just the same thing, and then if we put dx, we could do that. So we know the integral of 2x is x squared, and we could do the same thing if you really wanted to. But you can just do it all in one integral to save a bit of time, so you don't have to rewrite it. All right. So let's evaluate this. So we know that this is x to the first, and so you add 1 to the exponent, and then now with that new exponent you divide by that number. So you had x to the first, and then you added 1, so that's now x squared divided by 2. And then you subtract, and then we know that x cubed we're going to add 1, or x squared we're going to add 1, and then 2 plus 1 is 3, so we're going to divide by 3. And so this is going to be x squared, and then we're going to minus, because this minus sign stays the same, and then we're going to say x cubed over 3. And we can't forget the constant term. It's that easy. Let's do one more, and then we're going to learn something slightly different. Alright, so we now have the integral of x to the fifth, or the square root of x to the fifth with respect to x. So this is not the polynomial that we've seen before, but we can write this as the integral of x to the 5 over 2, because that's what a radical is. The square root is just something to the 1/2 power, and so we could rewrite this as the integral of x to the 5/2 with respect to x dx. And now this is like our polynomial that we had before. We can add 1 to the exponent and divide by that exponent. So 5/2 plus 5/2 plus 1 is 7/2. And then, so we might want to write this down. So 7 over 2. So this is what x is going to be to the power of. So I'll write that. And then we're going to divide by 7/2. When you divide by a fraction, you flip it. So you could just say 2 over 7. And then you can add the plus c. And it's as simple as that. Now we're going to do some integration with fractions, something like this, but I'm going to show you an algebra trick that will make this slightly easier for if you have something like this with one number on the denominator. And that's the key thing, is you have to have one thing on the denominator, so one term on the denominator. Okay, so this, you can rewrite this as x squared over 5 minus 3 over 5. Because when you add or subtract fractions, the denominator will stay the same if they have the same denominator, and then you just add or subtract the numerators. And so these two things are equivalent. And when before this would be kind of weird to integrate with our current understanding, we can do this, because we could just do the power rule to this, and we could do the power rule to this, and we could do our little integration trick. So now let's do a problem with this. Alright, so we have an integral here that we have one term on the denominator, so we can do our little algebra trick. So let's rewrite this. So this integral is the same as the sum of each of these little components. So let's look at this first part. 4x squared over x to the fourth. Well, we can rewrite this as 4 over x squared, because when you divide exponents, you subtract the powers. And so 2 minus 4 is 2, or is negative 2, so you have to have the x squared on the bottom. And then you can, but to make the integration even easier, we're going to say 4x to the negative 2, so that we can just apply the power rule and not have to move the exponent back to the top. So now we have this part, this 8x over x to the fourth. So it would be negative 8, and then we subtract the exponents. So x minus x to the fourth would be x cubed, but it's negative. So we're going to just rewrite this as, that is not an 8. Let's try that again. 8x to the negative 3, because we subtract the top from the bottom. And then the last term is 6. And so this is just 6. And there's no x's here, so it's x to the negative fourth. So 6x to the negative fourth with respect to x. We're integrating with respect to x. And now we have it in a form that we can integrate. And so we just apply our power rule, add 1 and divide by that exponent. Alright, so let's write that. So we have negative 2 plus 1 is negative 1. So we're going to say x to the negative 1. And then 4 divided by negative 1 is negative 4. And then we're going to subtract. And we're going to say, we're going to add 1 to the exponent. So negative 3 plus 1 is negative 2. So we're going to have x to the negative 2. And then we're going to say, and then we're going to have to divide by that power. So negative 8, because of this negative sign, divided by negative 2 is positive 4. So this is actually plus 4. And then we have this 6x to the negative fourth. So if we add 1 to the exponent, we have x to the negative 3. So we're going to not write the sign, we're just going to have, we know that it's going to be x to the negative 3. And then we're going to divide 6 by negative 3. So 6 divided by negative 3 is negative 2. So negative 2x to the negative 3. And then we got to remember to put the plus c. And then you could rewrite this if you wanted to, saying it's negative 4 over x, if you didn't want to have negative exponents. And then you could say this is 4 over x squared, and this is negative 2 over x cubed. And then plus c, if you wanted to rewrite it. But this is a valid answer. This is just to get rid of negative exponents. Now we're going to do one with trig. Alright, so with trig, it's a bit different, because you kind of have to think backwards to an extent. So let's start with thinking of the derivative of sine x. Okay, so you kind of have to know these. There's no real trick to memorizing them easier, or just kind of a rule. You just kind of have to know it. So we know that the derivative of sine is cosine x. And so, if we wanted to instead integrate cosine with respect to x, we know that by the fact that integrals and derivatives are opposites, we're going to get back to the sine of x, except just plus c. And we could do the same thing with knowing that the derivative of secant x is secant x tangent x. tangent x. And no, this is not inside. These things are multiplied together. Secant x, tangent x. And so if you wanted to integrate them with respect to x, we know that this would go back to secant x. So if you see some trig stuff, you want to try and put it in terms of a trig derivative so that you can easily integrate it. So now let's do a problem. Alright, so we have this integral of 5 cosecant x cotangent x dx. And so what we can do is we could say, hey, this 5 is a constant coefficient. There's no variable involved. So we can move this out front. So we don't have to worry about it until just shoving it in at the end. And if you remember that the derivative of cosecant is negative cosecant cotangent. So instead, if we know that because this is the inverse, not inverse as in like inverse function, but this is the opposite. It's negative of the derivative of cosecant. We could say that we know this integral is going to be a negative cosecant x. But remember, we took out this 5, so we have to put it back in at the end. So it's negative 5 cosecant x, and then plus c. And the reason I knew that this was negative is because if I took the derivative of cosecant x dx of cosecant x, this is equal to negative cosecant, that is, I don't even know what letter that was, cosecant cotangent x. And so because I knew this fact, that because if there wasn't a negative here, I would have to insert the negative at the end. Alright, so now we're going to use our knowledge of integrals and derivatives and solve this differential equation. We have a function's derivative, we have df dx, and we want to find f of x, the original equation of f. So what we can do is we can abuse, in a sense, the notation here. And so we have this fraction looking thing. It's not really a fraction, but we can call it a fraction for the purposes of differential equations. And we could move this dx to the other side by multiplying both sides by dx. So we could move this dx to this side. And so this is just df is equal to 10x to the fourth minus 5 dx. Alright, and so then we can integrate both sides to get rid of these d's, right? Or we can integrate both sides to get rid of these dx's and df's, because we just want this a function of x in terms of x, because it is a function of x. And so we know that the integral of something, of one item of that something with respect to itself, so like the integral of dx is just x, right? So we know that the integral of df is just f, but this is a function with respect to x. So we just have f of x. When you integrate df with respect to x, is just f of x. Okay, that's pretty easy. And now we can just use our power rule, right? So we can add 1 to the exponent. So plus 1, and then 4 plus 1 is 5, and so we can divide by 5. And then we have 5, and then an x to the 0 here, because this is negative 5, and then we have x to the 0. So we add 1 to the exponent, and then divide by 1. So this is just, let's see, 2x to the 5th minus 5x plus c. But we don't want this plus c. We have enough information to literally solve for the c value. So what we can do is we can say, we could substitute values in here and solve for the c value. So we know that f of 1, meaning substitute 1 in for x, is negative 9. So that's exactly what I'm going to do. I'm going to set negative 9 equal to 2 times 1 to the 5th minus 5 times 1 plus c. And then we're going to solve for the c value. So 1 to the 5th power is just 1, so this is just 2 minus 5 plus c is equal to negative 9. So this is just negative 3, and so negative 9, so this is negative 3 plus c, is equal to negative 9. I just combine like terms right there, and then I add 3 to both sides. That's negative 6 is equal to c. And all I did to solve for this was just substitute this into our equation that we integrated. I just realized this looks like 6 equals negative 6, which is not exactly true. Let's try that again. So this is what c is. And so now we can shove negative 6, we could substitute negative 6 back into this equation. So I'm going to rewrite this, and now f of x without, now that we know the constant term is 2x to the 5th minus 5x minus 6. Because this plus c is this, negative 6. Alright, so we're going to go look at properties of integrals now. Alright, so we have some information about some equations here. We have the integral of 1 to 5 of some function f of x with respect to x is 15. And some integral from 3 to 5 of that same function f of x with respect to x is negative 4. And so we want to find these three things. Alright, let's do this in green pen. So we have the integral of 5 to 3. That almost looks like this. And a property of integrals is saying if you have some weird bounds, you can, that is not like negative 5 to negative 10, you can flip these bounds by saying this is, so that you can actually just substitute in values. So this is going to be from negative 10 to negative 5. It's the same thing, just slap a negative sign in the front. They're the same thing. So we have the information needed from the integral, because the integral of 3 to 5 is negative 4. So we could say that from 3 to 5 is negative 4, so from 5 to 3, because they are flipped balance, is just going to be negative times negative 4, or just positive 4. This next one we see that the bounds of integration are the same. This is a 5 and this is a 5. And so if you want to find the area under a curve from this point to the exact same point, there is no area there. It is 0. It doesn't matter what the function is, and it could be negative 72 to negative 72. It is going to be 0 every single time because there is no area there. It's as simple as that. And so from here, on this last one, we're gonna use a different property of integrals. So we know that from 1 to 5 is 15. So if we wanted to kind of imagine this with a function, right? So from 1 to 5, this area is 15. I'll shade that in a different color. Let's say we know that this area is 15. And we know that 3 to 5 is negative 4. So that's probably not exactly a representative graph. So let's just something like this, right? So this is 5 and this is 1. And so we know that this area is this entire area. So this area minus this area is 15, right? And this area right here is negative 4. But if we wanted to find the area from 1 to 3, we could just subtract this area, because we can just remove it. The idea is that you can rewrite this integral as the integral of 1 to 5 f of x dx. I don't know why I added an extra little thingy there. Minus the integral of 5 to 3. Right? And so or no, 3 to 5. 3 to 5 of f of x with respect to dx. Because all we're doing is we're just subtracting this area. We're saying we don't want to go from 1 to 5 anymore. We want to go from 1 to 3. 1 to 3, right? And so we are subtracting off this negative 4 area, because we know that this from 5 to 3 is negative 4. So if we subtract the negative 4, you get 19. Because this is 15, and we are subtracting a negative 4. We are getting rid of the negative area, so the total area will increase. So it's 19. And it is simple as that. Alright, so let's do a sigma notation. So let's say we have the integral from something like 2 to 5 of x to the 6th dx. Now we could do this and substitute in values with power rule or whatever, or the inverse of power rule, but that's not what we're going to do. We're going to rewrite this using what a integral is. Okay, so an integral is the limit of a sum. Okay, so we're going to say as n goes to infinity. This is going to be how you will do all of these sigma notation problems. As n goes to infinity of a sum of, let's just call it k, I'm going to go from 1 to n. And so you will automatically know it's going to take the form of this every single time. This is the first thing you're going to do if a problem says rewrite this integral in terms of a limit. Great. We have how it's going to be, and so we're going to now just have something. And so let's try and imagine what the function would do. Okay, so we have a graph, and we know that this is not a 5, by the way, this is a 6. Let's make that more believable that it's a 6. There we go. And so now we know that this is a even-powered polynomial, so it's going to be doing something like that. And it's going to cross the x-axis at the origin because there's no other terms here. So the idea is that we're going to write this as a sum of areas, because that's what this is. And so we have little rectangles. If we said, let's divide it into, what is this, 3? The distance between 5 and 2 is 3. So what if we wanted to divide it into 3 equal sized rectangles? And those are relatively the same. And we could just say this one, and this one. And this would obviously be an overestimate. But you could add up these rectangles. Or what you could do is you could increase the number of rectangles by dividing it. And if we added up these little areas, and then you could see that there would be less of an overestimate than before if we did it, right? And so the idea is to say the number of rectangles is n. Just n is the number of rectangles. And we're going to multiply everything at the end by the number of rectangles minus the distance. So 5 minus 2 is 3. So 5 minus 2. If you tried to memorize the formula, this would be known as delta x. So, which is just the distance of, or the size of each thing. So this is just 5 over 3, or sorry, 3 over n. So this is just the size, the horizontal size of each rectangle. So if we were to zoom in on this plot, I can't physically zoom in on this plot, but I will redraw the graph zoomed in on like one rectangle. So we remember this was just like going up, but we're gonna say it's zoomed in, so we're gonna and so we want to zoom in right here. And so this width of the rectangle is what this is, because we divided it by the total length of the entire thing divided by n. So this is going to be the length of this rectangle. I cannot draw. Alright, so this length is delta x. And that's what this is. This length of a rectangle. And so you're going to have to multiply that by the end, right? Because you're going to say you want to add up every single area of a rectangle. And so the area of a rectangle is going to be width times the height. And so we now have the width of a rectangle. It's just 3 over n, or delta x. Alright, and so then you want to find the height. What is the height? The height is basically this point right here, right? So if we are trying to find, so we have this length, right? And so let's say this was 2 for in this case. So we know that the height is going to be, you have to substitute it back into the function, right? So if x to the 6 is f of x, right? So we'd say f of 2 plus what? This length, right? So we're going to say, what is the length? We figured that out. That is not a 3. 3 over n. And then what? And so if we had like another rectangle, right? The thing would change. This would change, and so we would have to keep doing this for each rectangle. So this, because this is k equals 1, k equals 2, and so on up to k equals 5. For however many rectangles there are. And so we would end up doing 3 over n times k. Because that's just the number of rectangles we're at. And so this is the height. The starting bound plus delta x times k. And so if we wanted this to be an area, this is the height. So this is, if we know the area is base times height, so this is equal to h, and this is equal to the base, right? And so we can substitute this back into our f of x equation. And so we have already written our base. So I'll write this in green, and I will write the height in red, or not red, this yellow, mustard yellow color. So we're going to say, what is f of this? Well, the function is just x to the 6th. So we're going to say 2 plus 3 over n. Let's rewrite that. 3 over n times k. This quantity all to the 6th power. And these two are the same, because this is the base of the rectangle, and this is the height of the rectangle. And we were summing infinitely small rectangles, because n is going to infinity. And so that's what the definition of the integral is. This summing of infinitely small rectangles. So now we're going to do some of the Riemann sums, but we're going to do a midpoint one because those seem to be a bit confusing to some people. So we're going to write an integral, and we're going to use the midpoint method to solve it, and then we're going to actually substitute in values and see how accurate this is. This should be pretty accurate, but it's not extremely accurate because it is just an estimation of the area. So we have this function, and we know that it is going to be a parabola, and it's because it is x squared. So we know it's going to be doing generally something like this. It's going to be, I don't know if it's going to be above or below the x-axis, and I don't know where it is exactly going to be. But it's going to do something like that. Actually, I do know it's going to be above the x-axis, but it's going to do something like that. But frankly, that doesn't really matter. We're just trying to find the area of this using some midpoint, right? And so this is 3 and this is -3. And so let's say 3 intervals, okay? So we know that the length is 6, so this is a distance of 3 minus -3, and we're going, because this is from the top bound to the bottom bound, so the distance is 6, and let's say 3 intervals. Alright, so divide by 3, and so the length of the interval is 2, okay? And so, like we saw in the sigma notation problem earlier, that would be delta x, if you wanted to think of it like that. So I guess I'll just leave that. So delta x is 2. The length of the rectangle is 2, right? So we have these little rectangles. If this is -3, this is 3, here's 0. Each rectangle is 2 long. And so the idea of midpoint is that we are going to find the value of the middle and add them together. So for each of these intervals, we're going to have one from -3 to -1, and -1 to +1, and 1 to 3. And so we're going to say, if this is f of x, right? So I'll just say this is f of x. We're going to add up. So we have x, and then we have the little f of x's that are in between. And so instead of doing the left side or the right side or whatever, we are going to do the middle point. And so the middle point between -1 and 3 is -2. So we're going to say f of -2. So f of -2 is going to be 3 times 2 squared, which is going to be 3 times 4, or 12. 12 plus 12 is 24, minus -2. So 24 plus 2 is 26. And if you wanted to write that out, you can. And try and work that out. And then the midpoint between -1 and 1 is 0. And so we don't have to worry about these x's because they're just 0. So it's just 12. So at x equals 0, f of x is 12. And at x equals 2, because that's the point between 1 and 3, we're going to say f of x is going to be 3 times 2 squared, which is 12, plus 12 is 24 again, minus 2, which is going to be 22. So at x equals 2, this is 22. Now, we have this height is 26, this is 12, and this is 22. But those are not the lengths of the bases. The base is delta x. So we have to say the total area under this curve is going to be 2 times 26 plus 2 times 12 plus 2 times 22. Because that is the length of the thing, right? Because we're taking this point and saying, here's f of x at this point, okay? And we're going to use this rectangle. And this is too wide, and we're going to add this area to this area, because this is the middle. And this is f of x at 2. And we're adding all of these areas together. And because the length is 2, we have to multiply, or the base is 2, we're multiplying everything by 2. And so, if I multiplied everything out to get a final answer, we would get 2 times 26, which is going to be 52, plus 2 times 12, 24, plus 44 is 120. So this is what we get by doing a midpoint Riemann sum. So let's just save that in the corner. And we're going to do more of definite integrals and at the end of the video. But let's instead see what would happen if we substituted this in when we actually integrated it. So we have our integral of -3 to 3. So we can do the power rule that we discussed at this beginning of the video. So we can add 1 to the exponent. So that's going to be 3. So x cubed. And then divide by that. So x cubed, and so that's just x cubed. And then we say minus, add 1 to the exponent, so x to the first plus 1 is going to be 12. Or no, I'm sorry, 1 plus 1 is 2, not 12. X squared over 2 plus 12 times x to the 0. So this is x to the 0 plus 1. So this is just 12x. 12x. And we do not need the plus c because we are going to, this is a definite integral. And so we're going to evaluate from -3 to 3. And so we're going to do top minus bottom. Alright, so we're going to just substitute in values. Alright. So we're going to substitute in values. So we have x cubed, and so we're going to say x is 3 in the first case, so this is going to be 3 cubed minus 3 squared. 3 squared over 2 plus 12 times 3. And so this is the top bound. This is the 3. And so then we're going to subtract the bottom bound because we want only -3 to 3, not -infinity to 3. And so we're going to subtract -3 cubed. So it's important that we remember that it's a -3 cubed minus -3 squared over 2. So -3 squared, no, that is cubed, -3 squared plus 12 times -3. Alright, let's see if I can do math. So 3 cubed, 27, but we're going to, so this is a -3 cubed, which is So this is 27 minus a negative 27 so this is actually going to be just two 27s because we're just minusing a negative 27. So I'll just say 2 times 27, which is going to be 54. So I'll just write 54. Alright, and then minus 3 times, so that's 9 over 2. So negative 9 over 2 minus 9 over 2. Or negative 9 over 2 plus 9 over 2 is just 0. So we don't have to worry about the middle terms. I'll cross it out in red because... And then we have 12 times 3 minus negative 12 times 3. Or 12 times negative 3. So 12 times 3 is 36. So 36 times 2. So 54 plus 26 times 2, if I'm doing all of my math right, 126, maybe? If I'm doing all of my math right. Let's just hope I'm doing my math right. And so 126, that's close. So this is, we got 126 with actual integration. And we got 120 with the midpoint method. So that's pretty accurate. So you can see that these are decent approximations. Alright, so let's look at some fundamental theorem of calculus. So we know that from earlier in the video that derivatives and integrals undo each other. And so if we take the derivative of an integral, we just get the original function. And if you integrate a derivative, you should get the original function with a slight couple of modifications. And so that's what we're going to see over here when we take the derivative of an integral. But over here, if we differentiate, if we would integrate this, we would do some fancy stuff, but we know we're differentiating an integral, so we could leave this pretty much the same. So we have 7, but instead we're integrating from 1 to x, and so the variable gets a name change to x. And that's about it. That's all this one is, because there is nothing else going on. Technically, you would have to multiply by the derivative of x with respect to x, but that's just dx, which is just 1. So if it's just something like this, you could leave it as 7x. So the derivative of an integral is the same thing with a couple of modifications. Just in this case, that modification is just a name change to the variable, because we were differentiating with respect to x, and we went from 1 to x. And so that one was easy enough. And so the second one is almost as easy, except we're integrating to x to the 4th. And so we have this really complicated looking integral. We have t to the t squared plus 1, the quantity to the 14th. And so if we were integrating that, we would have to do some other fancy stuff, and then we would have to go and differentiate that again. But don't worry, we're going to differentiate it right after integrating it, so we can use some simple tricks. So we know that we're going to get first a variable name change, but instead this t squared is going to be replaced with x to the 4th squared, because we are going to put x to the 4th in place of t, like we did before we replaced x instead of t. And so if this had been like squared or something, we would have put 7x squared, because we would just replace the t with x. But in here, we have x to the 4th times t squared, and so then plus 1 to the 14th. So if this was all we had to do, we would be done. But like I said before, technically you have to multiply by the derivative of this. And so the derivative of x to the 4th, using the power rule that we discussed, is 4x cubed. And now we are done. If you really wanted to, you could simplify this as x to the 8th plus 1 to the 14th. And polite math would say 4x cubed goes in front. But we are done. Differentiating an integral is not difficult. You just substitute in the bounds of integration. And if you were to have two bounds, like 3x and x squared of, and then d dx of like 4t squared dt. Let's go do this one real quick, actually, because we're going to, like I said before, we're going to substitute this in. So we're going to say 4 times t squared, which is now x, so x squared squared, or x to the 4th. And then multiply by the derivative of this, so that's just 2x. So we're just going to say 2x. And then we're going to do the same thing, but with the bottom, and we have to subtract it. So that would be 4 times 3, or 12, times, actually, I'm going to just leave it like 4 times 3x squared, because the whole thing has to be squared. So 4 times 3x squared times the derivative of 3x, which is just 3, and that would be that. And that is the fundamental theorem of calculus.